Okay, picking up where we left off here in chapter 5, just near the beginning here, we were talking about free body diagrams in the last segment of the video, and we saw some rules for drawing free body diagrams. And so I thought I'd include just a couple examples of some simple free body diagrams that you can draw. Say, for instance, for a box resting on a surface, you've got a couple of forces on the box if it's just sitting there. One is its weight pushing downward, and the other is the normal force pushing upward. That is the theoretical concept that, say, when you step on a floor, the floor is pushing up on you with the same amount of force that you're pressing down on the floor. And it seems an odd concept at first because you might think, well, the floor is not alive. How can it push back on me? How can it decide to do that? And well, it's not really that the floor is deciding to do that. It's that the floor has a certain amount of strength and it does that automatically when you step on it. Or at least according to Newton's laws, it must be pushing back on you with the same amount of force that you're pushing down on it. Because if it weren't, then you would be moving. Unbalanced forces result in not just motion, but acceleration. So if you stepped onto a floor and it didn't push back on you with the same amount of force that you're pushing down on the floor, then basically you would fall through the floor. And of course, as you fall, you accelerate, because that would be an unbalanced force. The downward force would be greater than the upward force. If somehow the floor managed to push up on you with greater force than you're pushing down on it, then it would launch you into the air. And you'd be, well, basically decelerating as you rise because of gravity. So there is this concept that basically anytime you have a weight pushing down on something, if that object is not falling, then you assume that there's a normal force pushing back up on it that amounts to the same amount of force. So that's what we have here. The free body drawing would represent the box as just a point that would be drawn at the center of mass of the box, which is where I drew the point here, actually. And so that point is not necessarily the floor. The floor in this diagram might be somewhere around there, where I drew that line. So this is the center of mass of the box, and you have the weight pushing down and the normal force pushing up. Weight is a force, and it is also equal to mass times gravity. That goes back to our old discussion about, mass is constant for any given object. It's a measurement of the amount of matter in an object. Weight, on the other hand, is affected by gravity. In fact, weight is mass times gravity. If you have a box at rest on an inclined plane, then what you would have might be something that looks like this. You've got the weight pushing downward, and you have the normal force. And this is kind of an important point. The normal force goes perpendicular to whatever surface you're working on. And so it's not necessarily normal to the earth. Normal is another word in geometry for perpendicular. It's not necessarily perpendicular to the earth. It's perpendicular to the surface on which the object is located. So in this case, the normal force would be perpendicular to the inclined plane. Looks like I'm not quite perpendicular there, but it would not be perpendicular to the ground. The weight always goes down perpendicular to the ground, or at least pointing toward the center of the earth. If the ground isn't level, then the weight might not be perpendicular to the ground exactly, but it does point toward the center of the earth. If the ground is level, then the weight would be perpendicular to the surface of the earth, if the surface is level. Drawing a free body diagram, again, we take the center of mass of the box as the center of the free body diagram. You have the weight going down and the normal force going perpendicular to the plane. And the other force, the third force that I haven't mentioned yet, is friction. Friction is a force that would resist motion in the direction that an object is moving or trying to move. If an object is sitting on an inclined plane like this, you would normally expect it to slide downward toward the earth because of gravity. But it's not, if it's at rest on the inclined plane, that simply means that there's enough friction to prevent it from moving. And friction would move in the opposite of the direction that the object is otherwise trying to move. And friction is a force, usually denoted by a small f with the vector arrow over it. But this line here that I drew in, that's the plane. The center of mass of the box is actually a little bit above the plane itself. So I just wanted to emphasize that. Okay, so looking into the idea of force, you could relate a force to a standard reference force like any other measurement. That's essentially what we do when we're measuring things like length or distance. We say that, you know, the distance from here to Rochester is 60 miles. That just means that we've got this standard unit called the mile, and it's of a certain length. And the distance between here and Rochester is about 60 of those. And we basically do this with force. One possibility is that you could use, say, the amount of force that it takes to stretch a spring as your standard. So if a spring is stretched to a certain distance, you could use the force it exerts when it springs back into its normal position as your standard. And then the magnitude of any other force could be related to that by just saying this other force is so many of those restoring forces for that spring. And, you know, you could give other forces in multiples of that force. But the usual standard for force is 1 Newton. We've mentioned the unit Newton before, but we haven't really said much about what it means. 1 Newton is equivalent to 1 kilogram meter per second squared, which is quite a mouthful. That's why they decided to call it Newton. And in other words, 1 Newton is a force that can cause a mass of 1 kilogram to accelerate at 1 meter per second squared. That's why the units are the way they are. You're causing a mass to accelerate. And that's basically what forces do. They cause masses to accelerate. And in fact, when we get into Newton's second law, we're going to find out that the mathematical expression of Newton's second law is F equals ma. Force is equal to mass times acceleration. And so the unit of force is a unit of mass, kilograms, times a unit of acceleration, meters per second squared. Only they just decided to call it a Newton just for convenience. And then we tend to state the magnitudes of other forces as multiples of or fractions of the Newton. Okay. Looking at another example, say a student sitting at a desk doing homework. The not necessarily physics homework. It could be, I don't know, what's the most unphysics-like thing you can think of? Ancient Greek poetry, maybe. Or no, they use the Greek alphabet for a lot of symbols in physics. So how about ancient Sanskrit poetry? That's it. That's what he's studying. He could be studying that. But even though he's not studying physics and he's studying something totally unphysics-like, he's still exerting physical forces that we can use physics to analyze. And so we might wonder, what are the forces acting on him and what are the origins of those forces? Well, forces in general are grouped in a couple of types. One type is contact forces, and the other would be field forces. Contact forces are, like the name implies, they require direct contact in order to work. And the forces in the diagram would be things like that require contact to work would be things like, well, in general terms, not just in the diagram, but in general terms, the push or pull or friction would be another example. And in the diagram, let's see, the diagram is on page 211. there's no way I could draw this, so I'll just show it here. Okay. So this is the diagram we're talking about here. So we have various forces. Okay, so the force on the table, the force of him leaning on the table, that is a direct contact force. The force of the floor pushing up against him, that's a direct contact force. There's the force of the chair pushing up on him, that's a direct contact force, and so on. All right. Okay, so basically the chair pushing up on him, the floor pushing up on him, and him leaning on the table. Those are direct contact forces. There are also field forces. Field forces are forces that work remotely without direct contact. And basically all you have to do is be in the presence of a field of this force to experience its effect. And some of those would be like gravity. If you're in a gravitational field, that is, if you're close enough to an object with sufficient mass, then you will experience a gravitational attraction toward that mass, and that is a force. It's a force that acts, though, even if you're not in direct contact with the object. You know, the Earth has enough force for this pen that I can drop it, and that force will take over and pull the pen down to the Earth. Even though the pen's not in contact with the Earth, it's still experiencing that force. And so that's why it dropped. Electromagnetic forces like static electricity, or positive and negative charges, or north and south poles of magnets, those work at a distance. So, you know, we've probably all played with magnets from one time or another. You can put one magnet down with the north pole facing one way and another magnet down with the south pole facing it. And even if you put them a certain distance apart, they'll snap together, because that attraction works over a distance even when they're not touching each other. If you put a magnet down with a north pole and a north pole, you can actually force them to touch each other, and you let go and they'll push themselves away from each other. So that repulsion works even when they're not touching each other. So that's definitely a field force. The strong and weak nuclear forces are field forces as well. The force in the diagram labeled W, which is the force of his weight pushing down on the chair. Weight is considered a field force because it's caused by gravity, and gravity itself is also a field force. Let's see. These field forces tend to work only over a certain distance. And for some of them, that distance is greater than others. So gravity works over a pretty fair distance, depending on also how far a distance gravity works over. Depends largely on how great the mass of the objects are, and how strong the gravitational attraction will be. But also things like electromagnetic forces work over a much shorter distance. In fact, electromagnetic force is inversely proportional to the square of the distance between the two objects, which means if you double the distance between two objects, you cut the electromagnetic attraction by a factor of 4. And these strong and weak nuclear forces operate only over a very, very short distance, that's within the nucleus of an atom. And so we don't really consider the nuclear forces in any detail in this chapter, because they're working at a scale that are much smaller than Newtonian scales. Like I said, Newtonian physics doesn't really work at any level below about the size of an atom. Technically, if you want to get really down into the theory of things, most contact forces are also electromagnetic forces at the smallest level, but that's also smaller than Newtonian scales, so we don't really need to go into that. Okay. Looking at vector notation for force, as I mentioned, force is a vector because forces do have magnitudes and directions. The SI unit for a force, as I mentioned before, is the Newton. That just means that Newton is sort of the reference quantity, and we relate other forces to it as either a multiple or a fraction of a Newton. And it's equivalent to 1 kilogram meter per second squared. In other words, the force required to accelerate a mass of 1 kilogram at a rate of 1 meter per second squared. And in terms of downward force caused by gravity, 1 Newton would be about the weight of a small apple. So that's about how much force a Newton is. It's not very big, so a lot of forces come out to have a very large number of Newtons. In vector terms, you can represent a two-dimensional force as being some number times unit vector I plus some number times unit vector j. In 3 dimensions, it would be the same idea, except you would add in some other number times unit vector k for the z direction. If you were to look back on the example of the ice skaters in figure 5.3, the ones where we had person 3 being pushed by person 1 and person 2, like so. And we expect person 3 to go off in that direction with some amount of force. If, say, skater 1 pushes on skater 3 with a horizontal force, I think actually, if you're looking at this from the ground level in 3 dimensions, of course, all of the forces are horizontal. I think they were talking about horizontal in the diagram. So let's say x direction force of 30 newtons. And to the right, that is. Okay, so F1, that is the force of person 1 pushing on person 3, is 30 times unit vector I newtons. If skater 2 pushes skater 3 with a vertical, I think, again, what they mean is vertical on the diagram, but of course it would be horizontal in person. So we're going to call this a y direction force of plus 40 newtons. Then F2 would be 40 times unit vector j newtons. And the resultant of the forces on the skater, on skater 3, causes her mass to accelerate. She has a certain mass. Those forces will cause her mass to accelerate. And the forces on her would be known as the net external force. So that would be the total of F1 and F2. So the net force is the vector sum of all the individual forces. That is the external forces. We don't normally deal with internal forces on this scale, or at least on the Newtonian scale of motion, because internal forces usually don't affect the motion. And so the net force will be just the summation of all the forces, or F1 plus F2 plus yada, 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 yada. In this case, this example, F net would be, sorry, that should be a vector, 30 times unit vector I plus 40 times unit vector j. The magnitude of the force, again, this is the vector equation telling you how big and in what direction the forces, the net force would be. If you want the magnitude of that force, it would just be the square root of the x term squared plus the y term squared. And that turns out to be 50 newtons. And if you want to know the direction would be the inverse tangent of the y term over the x term, and that's 53.1 degrees from the x-axis. And so that would be the angle there, 51.3 degrees. If the skaters were in the same situation and were pushed with different forces, say their forces are not along the axes, then you would just add the vectors the way we normally do. Add the I terms and add the J terms. So F1, if F1 is 3 times unit vector I plus 8 times unit vector J newtons, and F2 is 5 times unit vector I plus 4 times unit vector J newtons, then F net would just be 3 plus 5 times unit vector I plus 8 plus 4 unit vector J, or 8I plus 12J newtons. And the magnitude would be basically 8 squared plus 12 squared, take the square root, that's 14.4 newtons. And the direction would be inverse tangent of the Y term over the X term. So that's inverse tangent of 12 over 8, that's 56.3 degrees. Okay, so that's not too difficult. And finally, we can get to Newton's laws. This is the section 2 of the chapter. Now that we've built up some terminology and some concepts, we can actually get into Newton's laws. Newton's first law also known as the law of inertia. And inertia is just that things like to, in terms of motion anyway, things like to stay the way they are. If things are moving, they like to keep moving. And if they're stopped, they like to stay stopped. Of course, that's a very general description, and we'll have to get into a little more detail here. A body at rest remains at rest, and a body in motion remains in motion at the same speed in the same direction, that is, unless acted upon by some outside force. And that is what inertia is, resistance to change in motion. Okay, so that's how you could, that would be a good working definition for inertia. This assumes no friction or air resistance, especially when you think about the body in motion. I mean, certainly even here on Earth, where there's plenty of air resistance and friction, something that's sitting still will tend to sit still basically forever unless some exterior force comes and acts on it. So I could put this pencil here, and it's going to sit there basically forever until something comes along and changes it. Somebody comes along and moves it, or maybe the 100 years from now, when nobody's been living here and the pencil's still sitting there, the ceiling caves in and knocks it on the floor, or something like that. But that would require an external force. Otherwise, it's just going to sit there. But a body in motion remains in motion unless some exterior force comes along to change that. Well, friction and air resistance are external forces. And so that even if you allow for friction and air resistance, Newton's law still applies. So a body that's in motion, say if I were to take a level tabletop and like give a marble a little push and have it start rolling across the table, it will eventually stop. And you might think, oh, well, Newton's law doesn't apply to that because the marble stopped. Well, the marble stopped because in that case, and it's something the size of a marble and at the speed that they would tend to move, it's probably friction that stopped it. If the marble were moving really fast, maybe air resistance too. But those are external forces. And it says right there, unless some external force causes it to change. If you took the marble to the International Space Station, where there would be no friction and no air resistance, or actually, well, put it out into, say, outer space, there's air inside the space station. But if you flick that marble out the door of the space station into outer space, where there's no friction and no air to resist its movement, it would keep going at the same speed forever, literally forever, unless it hits something. but hitting something would be an external force, and so that would still qualify under Newton's laws. Or in other words, another way of stating Newton's law is that there has to be a cause for any change in velocity. Okay, which would include like things like friction or air resistance or hitting something else. Okay. Newton's first law is universally applicable. It works, actually, this particular Newtonian law works pretty well even on subatomic scales. And so it basically applies to everything everywhere. It applies to everything on Earth. It applies to everything in space. It applies to everything big and small alike. Now, looking at the idea of gravity and inertia, gravitation, which is kind of a fancy term for the concept of gravity, is basically an attraction between objects based on their masses and also on their distance of separation. But the mass is kind of the most important factor there. The magnitudes of the gravitation, like it says, depends on the masses of both objects involved, but gravitational attraction is usually very small unless one or both of the masses are really, really large. I could take, say, this pencil, and I could take this other pencil, almost identical, and say, because these pencils both have mass, there is a certain gravitational attraction between them. But the masses of the pencils are very small, so the gravitational attraction between them is extremely small. It's not even enough to overcome the friction of moving them along the paper to bring them together. So that's a very, very small gravitational attraction. On the other hand, if you take the gravitational attraction between this pencil and the Earth, well, the mass of the pencil is still very small, but the mass of the Earth is pretty freaking large. And so the gravitational attraction between this pencil and the Earth is very substantial. If I let go of it, it's going to drop. And it's going to drop until it hits something like the paper or the table or the floor or the Earth, until something stops it. But that's a much greater gravitational attraction because of the mass of the Earth being so big. Gravitational attraction is a force. And in fact, the gravitational attraction between any object and the Earth is generally referred to as the object's weight. Okay. So the fact when I feel this pen, or pencil, even though it's small, I can feel it pulling down on my hand. That's the gravitational attraction to the Earth that I'm feeling there. In other words, I'm feeling the pencil's weight. Okay, so inertial reference frames. This is a little complicated, so I won't spend a lot of time on it, and I don't think it's really supremely important, but we can always set things up in terms of our reference point so that the net force on an object is zero. It really all depends on how you look at it or what point of view you're using. And if the velocity of an object relative to a reference frame is constant, and remember, zero as a velocity would qualify as being a constant velocity, then the reference frame is inertial. So inertial reference frames are ones where the relative velocity of the reference frame and the object is constant. It's not necessarily zero difference, but it could be a constant difference. Inertial reference frame is any reference frame for which Newton's first law is valid. Okay, so that's why the reference to inertia. And Newton's first law involves objects at constant velocity, and keeping in mind that constant velocity would include zero velocity. So in other words, something that's not moving counts as being at constant velocity. So any reference frame moving at constant velocity relative to an inertial reference frame is also inertial. So it's sort of like multiple reference frames, but as long as they're all moving at constant velocity relative to each other, or in other words, no acceleration allowed, then they're all inertial relative to each other. Any reference frame accelerating relative to an inertial reference frame is itself not inertial. Okay, so, and actually, as it turns out, any reference frame that's at rest relative to, say, very distant objects that don't appear to move very much can be considered inertial. But that doesn't mean that you could put a spot on Earth and say, okay, this spot here is not moving, and there, so therefore it is an inertial reference frame for that star that I'm looking at off in the distance. That actually isn't the case because, of course, the Earth is moving relative to that star. You could pick a stationary point in space, say above the Earth, and that could be an inertial reference frame for that distant star. But if it's on the surface of the Earth, it's going to be moving relative to a distant object, so that would not apply, actually. Okay, but often that's close, often that's close enough, at least over a period of time, depending on how long a time you're planning on observing things. So actually, reference frames fixed to the surface of the Earth are generally considered inertial in this book. Okay, so for what that's worth. Okay, Newton's first law relates to equilibrium also. Equilibrium is a state in which all of the forces on a system are balanced with each other. So if we took the example of the three skaters from earlier, they were not in equilibrium because you've got skater 1 pushing on skater 3 in this direction, and skater 2 pushing on skater 3 in this direction, and that results in some movement in a third direction. And the fact that those forces result in an acceleration, that is, the skater 3 starts out standing still and ends up going a certain speed in a different direction, that would be an acceleration. So the fact that these forces on skater 3 cause an acceleration, that tells you right there that those forces are not balanced. If the forces were balanced, there would be no acceleration in skater 3. Okay, so in other words, the net force or the resultant force on skater 3 is just going to be the force exerted by skater 1 plus the force exerted by skater 2. And for equilibrium, what we would need would be a counteracting force to balance F1 and F2 and make F net or FR, resultant force, 0. And what you would need for that would be basically figure out what the resultant force is, and what you would need, or the resultant force vector is, and what you would need would essentially be the opposite of that. So if the resultant force in terms of the vectors is 30I plus 40J, then negative FR would be negative 30I minus 40J newtons. Or in terms of the magnitude, we said the magnitude of the force was, where is it here? Yeah, the magnitude of the resultant force was 50 newtons at an angle of 53.1 degrees from the x-axis. What we would need would be a force of 50 newtons at that same angle, but pointing in the opposite direction, going that way. If you push in the same direction with 50 newtons of force in the opposite direction of the resultant force, then you would stop skater 3 from moving. And that would be enough to balance forces 1 and 2. So this brings us to the vector form of the first law, and that is the velocity vector is constant if the net force vector is 0. But remember, again, 0 meters per second would be considered a constant velocity. So the velocity, the object could be at rest. All right, so, for example, a car sitting at rest has only the force of the weight downward and the contact force of the pavement upward, which balance out, and they're equal. So the car doesn't accelerate. It's sitting there at rest at 0 meters per second. That's a constant velocity. If a car is in motion, though, you might wonder, do the forces balance out? And the tendency would be to say that because the car is moving, then the forces must not balance out. But actually, what Newton is saying is that unbalanced forces result in acceleration. There can still be movement when all of the forces are balanced. It's just that that movement would have to be at a constant velocity. So if a car is in motion at constant velocity, it still has its weight downward and the contact force of the road pushing upward, which balance. It also has the engine or mechanical force pushing it forward, but it also has friction and air resistance pushing it backwards. And if the velocity is constant, those must balance also. So the velocity would be constant at something greater than 0 meters per second because it's in motion. If those forces were unbalanced, say if the engine force driving the car forward were greater than the total of the friction and the air resistance, then the car would be accelerating. If the engine force were less than the total of friction and air resistance, then the car would be decelerating or accelerating in the negative direction. Okay, so hopefully that makes something clear anyway. I think we've probably gone over time now on the video, so I'm going to stop there and we'll get to Newton's second law next time. So until then, I'll see you later.